the third session for today. So we have 5 talks to go through, starting with 2 ATLAS talks and then 3 talks on future plus, minus, colliders, CLIC, etc. So we start with Aleksander Leopold on searches for dark matter produced in association with the Higgs boson, reporting ATLAS results. And thank you, Aleksander. I can already see your slides.
Hi, can you also hear me?
Yeah, we can also hear you. Please go ahead.
Okay, great. Then hello, everyone. My name is Alex, and I'm happy to present these ATLAS results today on searches for dark matter produced in association with the Higgs boson and invisible decays of the observed Higgs boson. Now, as you're all aware, there's strong evidence for dark matter coming from astrophysical and cosmological observations that we find on different scales from galaxies over galaxy clusters up to cosmological scales. But while we have all these nice results on the basis of gravitational effects, the fundamental nature of dark matter is still unclear. Now, in the laboratory, there are 3 complementary strategies to search for dark matter particles. There's direct detection, there's indirect detection. And at colliders, we have the possibility to create dark matter particles if those are kinematically accessible. Of course, those are then not expected to leave any observable signals in the detector, leading to missing transverse momentum signatures. Now, missing transverse momentum, or MET, is basically a momentum imbalance in the transverse plane, which in ATLAS is reconstructed as the negative vector sum from all the hard objects in an event, which can be jets, taus, muons, photons, or electrons, and the so-called soft term, where we use tracks that are associated to the primary vertex, but to none of these hard objects. Now, if we want to produce dark matter particles at the LHC, of course, we need some kind of connection other than the gravitational force between the standard model and the dark sector. And what I'm going to discuss today is the possibility that this connection is made by the Higgs sector. So I'm going to discuss 2 different possibilities here. So either extended Higgs sector portal models, where you then expect dark matter to be produced in association with the Higgs boson, or so-called Higgs portal models that would lead to invisible Higgs decays. I'm going to start with the first kind, so extended Higgs sector portal models, where the benchmark simplified model of high interest at the moment is what I will refer to as a 2HDM plus A model, which is based on a 2 Higgs doublet model. So you have 5 observable Higgs bosons in that. Plus the model also contains an additional pseudoscalar, the lowercase a, which is the one that actually then couples to dark matter. One interesting part of this newer model is that it has actually quite interesting and rich phenomenology. So you have many different signatures that can be compared and combined, as I'm showing here, for example, on this plot on the bottom right from the 36 inverse femtobound results, comparing different channels, looking for this model. One other thing to note is that there are 2 production modes that also have an influence on the event kinematics, gluon-gluon fusion or BB bar associated production, where which of those is the dominant one depends on this tangent beta parameter, which is the ratio between the vacuum expectation values of the Higgs doublets. Another benchmark model that is used is a Z prime 2HDM model, which also contains an extended Higgs sector plus a new vector mediator, Z prime. Now, even though this one is already quite strongly constrained by Dietrich searches as well as B physics results, it's still in use as a benchmark model, and it's especially interesting for very highly boosted regions. Now, the first result that I'm going to talk today about is the mono Higgs to BB bar search, which looks for dark matter produced in association with the Higgs boson, where the Higgs is reconstructed from the BB bar decay, which is done by selecting events that contain at least 2 B-tech jets and also contain large missing transverse momentum. Now, the main backgrounds here come from TT bar as well as W and Z production in association with heavy flavored jets, for which rejection cuts are applied, and also cuts are applied in order to reject fake MET coming from mismeasurements. In this analysis, the signal region is split into a resolved and a merged region, depending on missing transverse momentum. This is done since in the highly boosted region, the reconstruction of a B-jet pair from 2 jets is actually quite challenging. So those are reconstructed then as a large R jet. And within those large R jets, then the B-tagging is done using track-based jets. One thing to notice also that this result includes as a first 3 or more B-tag category, which has a specific sensitivity to the high tangent beta region, where then the BB bar associated production is dominant. The results are obtained by simultaneously fitting the signal and control regions, where the fitted observables in the signal region is the reconstructed Higgs mass and the missing ET. And this analysis basically looks for an excess of events around the 125 GeV Higgs boson. So no significant excess was observed, and the results are thus interpreted as upper limits. And you can see these here visualized as exclusion curves. On the top right for the Z prime 2HDM model, where Z prime masses up to around 3 TeV can be excluded. And in the bottom, those are the results for the 2HDM plus A model. On the right-hand side, for low tangent beta values, where GGF is the dominant production mode. And you can see the increase of the exclusion compared to the previous result. And now with the new 3 B-tag category, there's also a first result now that is more sensitive to the high tangent beta region, where you can see that here the exclusion is up to around 220 GeV for the lowercase a pseudoscalar. There's also the mono Higgs to gamma gamma analysis, which provides complementarity with the Higgs to BB bar search. Here, one specific thing is that since the Higgs is reconstructed from 2 photons, this analysis can use a diphoton trigger instead of a mass trigger, which gives it a unique sensitivity in the low MET range between 150 and 90 GeV that the Higgs to BB bar or the mono Higgs to BB bar analysis cannot reach. Of course, then events are reconstructed with at least 2 photons and MET in the events. In order to reject the backgrounds, so there are cuts applied in order to reject fake MET, as well as those applied in order to reject some of the standard model backgrounds like V gamma and V gamma gamma. In this analysis, the categorization is performed using a boosted decision tree that only uses 2 input variables, the missing ET significance as it is defined here, and the diphoton PT. And these found categories are then visualized here on this plot on the right-hand side that shows the BDT score as a function of the missing ET significance and the diphoton PT. In this analysis, the results are obtained from an unbinned fit on the invariant diphoton mass. So in order to do this, the individual contributions need to model with analytical functions. So for the peaking standard model background and deep signal, this is done using double-sided crystal ball functions, while for the non-resonant background, smoothly falling function is chosen. Again, no significant excess is found, so the upper limits have been set and exclusion curves are here. I'm showing here 2 results, one on the top for the 2HDM plus A models, where lowercase a pseudoscalars up to around 250 GeV can be excluded, and for the Z prime 2HDM model, where Z prime masses up to about 1.35 TeV are excluded. Okay, now moving to the second part, so the invisible Higgs decays. Now, in the case that dark matter particles mass is lower than half of the Higgs mass, the Higgs could potentially decay to dark matter particles, and thus giving this invisible signature. There's also a standard model invisible Higgs decays, but those have very low branching fraction, in order of 0.12%, while in some of the BSM models, those branching fractions can increase up to around 10%. In terms of the production modes at the LHC, of course, the gluon-gluon fusion is the dominant one at the LHC, but for this kind of searches, experimentally quite challenging, while the vector boson fusion is more interesting here, since with the additional pair of the quark-induced jets, selecting on those signatures improves the signal over background ratio for these searches. The first result that I would like to show here is the VBF Higgs to invisible plus photon search, which came out quite recently and is actually a first in this final state for ATLAS, where I'm selecting this final state with the additional photon actually allowed to improve the background rejection as well as the signal reconstruction efficiency. The dominant backgrounds then come from Z gamma plus jet as well as W gamma plus jet production. There's also a standard model Higgs decay, which has the same signature, but here the contribution is so small that this was neglected in this analysis. In order to select events now, to select this VBF topologies, events are selected that have large invariant mass of the dijet, large pseudo rapidity separation between them, and also have large missing transverse momentum. And of course, also in this analysis, they are looking for an additional photon, which is required to be found centered between the two jets. For the event classification, a dense neural network is used, and the categories are then selected based on the DNN output. Control regions are defined in order to constrain the background, and the results are obtained by a simultaneous fit on all the signal and control regions. And in this analysis, the upper limit on the Higgs to invisible branching fraction was extracted to be 37%. Now there is an additional interpretation that was provided by this analysis, which is a Higgs to photon and dark photon search, where instead of the DNN for the event classification, the transverse mass, as it's defined here, was used. This has this very specific distributions for the signal, depending on the Higgs mass here. And here again, a simultaneous fit was performed, and upper limits have been extracted, which allow to exclude Higgs masses up to around 2 TeV. Now, there's of course also the VBF Higgs to invisible search, which again has a similar event selection, where you select for large invariant mass, large pseudo rapidity separation between these quark-induced jets, as well as large missing transverse momentum. Here, the 11 signal region bins, which use the dijet mass, the number of jets, and the delta phi between the jets for the binning, in order to constrain the backgrounds, which are then V plus jet backgrounds, as well as multi-jet backgrounds. Specific control regions have been designed, and the results have been obtained by a simultaneous fit. Here now, of course, for the full run 2 results, where the observed upper limit is now 13% for the VBF Higgs to invisible channel. These results have also been interpreted in terms of WIMP nucleon cross sections as a function of the WIMP mass in order to compare them with direct detection experiments. And you can see that these results get competitive in the very low WIMP mass region, but of course, these kind of comparisons always come with some caveats. On the right-hand side here, I'm showing the main uncertainties that go into this analysis, where the main ones come from the estimation of the multi-jet background, as well as from Monte Carlo and data statistics. Of course, all of the different channels that can be used for looking for invisible Higgs decays can be combined. And in this full run 2 combination, there are three inputs. The first one is the Higgs to invisible search that I just presented. The second one is a search for invisible decays of the Higgs boson in the TDH topology, which is actually coming from a reinterpretation of a SUSY result. And the third input to this combination comes from the run 1 combination. And from combining these 3 results, the observed upper limit could be brought down to 11% now on the branching ratio of the Higgs to invisible decays. And you can see here that the strongest individual constraints in this combination comes from the VBF Higgs to invisible search. So, and with that, I will come already to my conclusions. So I've shown you some of the full run 2 searches for dark matter produced either via Higgs boson or in association with the Higgs bosons. So there have been new results in mono-Higgs signatures, both in the BB bar as well as in the diphoton channel. I've shown you a new Higgs-2 invisible plus photon analysis, which was performed in ATLAS for the first time. The upper limit on the Higgs-2 invisible branching ratio has been improved in the new combination to an upper limit of 11%. And of course, more exciting results are continuously coming out. And those will then allow, of course, to further explore the parameters space. Please also see the talk that is following mine for more interesting results. And yeah, maybe the Higgs boson can at some point help us to understand more of the properties of the dark sector. So with that, I'll finish, and thank you for your attention.
Thank you, Alex. Thank you for these nice slides and also being right on time. Are there any questions for Alex? Please raise your hands. Maybe one quick question I can ask while we are waiting. For the VBF Higgs invisible results, I was wondering about the triggers. Is it just missing energy, or is it also using...
Right, so the signal region is using a MET trigger, that's right. And for the control regions, then different triggers are also used.
Okay, like forward jets and those kind of...
Yeah, lepton triggers and jet triggers for the jet trigger for the multi-jet background, if I remember correctly.
Okay, okay, I see. And then maybe one quick question on I think this was on slide 8 for this 2 HDM plus A model. Yeah, this is, I'm not really familiar with this model, but when you give this kind of limits of M of mediator on the y-axis and then on the x-axis is the small a. So the parameters here, they're basically independent from the 2 HDM kind of model parameters that determine the masses of heavy Higgses and things like that, or they are somehow all connected together?
Well, I mean, it's compared to, for example, the Z prime 2 HDM model. This model is a bit less simplified, let's say. So you have more parameters that determine also your kinematic, your event kinematics. So if you look in the conf notes or in the papers, you will see that several different scans have been performed in different planes for this kind of models.
Okay, thanks. Tanya, you have a question or maybe a comment?
Yeah, it's a comment, in fact, on your question. So there's this beautiful diagram on the top here with the A being produced on the S channel and then decaying to AH and the 2 size. So just to explain to you the difference to the 2x doublet models, I mean, the coupling of so basically what you do is you add this little a and then you introduce a mixing between the big A and the little a. So you have one additional mixing angle, yeah, which determines the couplings, for example, also to the size. Then there's an additional coupling. So in a sense, you have 3 additional parameters here in this diagram. And I think what is typically done is that there's this white paper by the Dark Matter working group, which suggests what to do. So there are 12 parameters in total, and they tell you to fix 10 and then do 2D scans. And I think this is what is happening. So in principle, it would be nice to go away. Maybe this is now a comment to the experimental analyses, to go away from these benchmark points and to try at least to see how these results are varying if one sets some of the other parameters to different values, because this is, I mean, this is the typical discussion also for SUSY, you know, where you fix everything but 2 parameters and then you show plots. But in a sense, this is really only okay with this particular choice of other parameters fixed. So this would be interesting to see.
Yeah, definitely. I mean, as I mentioned, there are several of these scans that are performed by the respective analysis, but yeah, there's a limit to what is done and what potentially could be done.
Yeah. I mean, it's good to compare then, you know, how good is the H going to BB plus MET versus H going to gamma gamma plus MET, then you can more or less immediately compare these two plots if everything is the same. But the danger is, as always, that then people say this model has been excluded up to masses of. And
Yes.
I mean, you know, these diagrams where we all see that everything below 3 TeV is excluded, and this is just, one has to be a bit more specific. I mean, it's not a criticism, it's a comment. Yeah, okay, thank you.
Sure, yeah, thank you, Tanya, for discussion, and thanks again, Alex, for this nice talk.
Thanks a lot.
Okay, now we move to Guglielmo Frattari, who will continue telling us about dark matter searches with the ATLAS detector.
Hello, can you hear me?
Yeah, I can hear you, and I also can see your slides.
Okay, thanks a lot. So I will start. So hello, today I will continue talking about dark matter, and will show you some recent results on simplified dark matter models. And let me go full screen. Okay, as I said, this talk will be focusing on simplified dark matter models, and more extended results have been already shown by Aleksander, and other interesting models will be shown by Abhishek. But today I will be focusing on these ones. So the question is, why simplified dark matter models? So the idea is to somehow go beyond the effective field theory approach, which was carried out during round 1 of the LHC. And these models are called simplified because they are introducing a new mediator and fermionic WIMPs. And in general, they are described by only few parameters. In particular, they are described by the mass of the WIMP, the mass of the mediator, and the coupling between the new mediator and the standard model particles, and the new mediator and the dark matter particles. So what we expect to see from this kind of models are mono-X final states, like the one which can be seen in the diagram in the bottom left, in which you have that the invisible part of the diagram, so the WIMPs are recoiling against initial state radiation, or we could look for the resonant production of this new mediator in dijet final states, and we would expect to see a bump in the MJJ spectrum in this case. Or we could expect to see an overproduction of heavy flavored plus MET final states. So starting with the monojet search, this is the most general signature that one could think for looking for beyond the standard model particles. And the goal here is to look for an excess of events in the MET distribution, which is also the discriminant variable of this search. So the events are selected by looking at events with at least one energetic jet recoiling against a large missing transverse momentum. And this kind of search is, of course, dominated by the background, which is the production of a Z boson decaying into invisible final states in association with jets. So the idea here is to control the backgrounds as more precise as possible in order to look for any excess either on detail or at low missing ET. And to do this, higher order correction are applied to the V plus jet processes by following the prescription from the paper linked in the slide. And this kind of prescription allow us also to correlate the estimate of the Z plus jet and W plus jet processes in the fit. So in order to adjust somehow the Monte Carlo prediction of this kind of backgrounds, some contour regions are defined by inverting the lepton veto, and this is done in order to emulate the kinematics of the signal region. And in order to better emulate this, the leptons are treated as invisible particle, and so we might emulate as best the Z-nu process. So a simultaneous likelihood fit is performed then to the regions in order to estimate the signal region background. And as I said, one single normalization factor can be used to normalize the V plus jet processes, while the top quark backgrounds are, the modeling of the top quark backgrounds are corrected in a dedicated control region. So on the left, you can see a plot which is summarizing the effects coming from different sources of systematic uncertainties, and these are compared to the data statistical uncertainty, which is shown by the black points versus the missing ET. So you have also in the red dashed line the total signal region uncertainty, and you can see that this is ranging between 1.2 and 4%, and this can be further split into effects which are coming from detector uncertainties or modeling uncertainties. So in the top pad, you can see the effect of detector uncertainties, detector related. And as you can see at low missing ET, the estimate of the multi-jet background is yielding a large systematic uncertainty, while at large missing transverse momentum, the uncertainties coming from leptons and jets measurements are dominating. While in the bottom pad, you can see the modeling uncertainties, and in particular, you can see how the modeling uncertainty on the V plus jet processes are, of course, the dominant one. So on the right, you can see the distribution of missing transverse momentum in the signal region, and as you can see, how a good agreement with the standard model is achieved. So another way to look for this kind of models is to look for an excess over the MJJ spectrum, and here the main challenge is to model the standard model QCD backgrounds. So as I said, we want to target simplified dark matter models like the one on the left, in which a mediator is produced through S-channel interaction in a resonant way. So these kind of searches are targeting the values of MJJ greater than 1 TeV due to limits in the trigger thresholds. And then in order to enhance the sensitivity to this kind of signals, a cut on the rapidity gap of the leading jets is applied. Then the background is estimated via this technique, which is called the sliding window fit, which is a technique well known and is tested on pseudo data in order to find the best fit function. And then once this function is fixed, it is looked at the real data. So the function which is used to model the background is the one represented in the slide. And an uncertainty is coming from the choice of this kind of function, which can reach up to 10% on the background estimation in the high MJJ, of which you can see a plot on the right. So other background uncertainties are coming mainly from the statistical fluctuation of the fit parameters of the function, and this can be very high, up to 30–40% at high MJJ, while negligible contributions are coming from spurious signal tests. So in order to evaluate the significance of the deviation, it is adopted this algorithm, which is called the bump Panther, which is sliding along the MJJ spectrum and looks for any excess, and then it evaluates it in a global way. And as you can see, no significant deviations are observed. So one can look at the constraints which can be set by these two searches and others on the parameters of the simplified dark matter models. And in this slide, I'm showing you the limits which are set on models considering a vector mediator. So if you look at the plot on the left, you have on the x-axis the mass of this new Z prime mediator, on the y-axis the mass of the WIMP, and this plot is obtained for fixed values of the mass of the couplings, but also different coupling scenarios are tested, and you can find a plot in backup on these. So as you can see, the mono-X searches are mainly sensitive in the on-shell regime, and among the mono-X searches, you can see how the mono-jet search is the most sensitive one, while the resonance searches are, of course, able to explore also the off-shell regime, since you are looking only at the resonant production of the mediator. So these kind of results can be converted into direct detection, into limits on the interaction cross-section between the WIMPs and the nucleon. In particular, when considering a vector mediator, one can look at the spin-independent interaction. And you can see how the ATLAS results are comparing to the direct detection experiments in the right plot, in which you can see that the direct detection experiments are able to set more stringent limits in the range between 10 GeV to more than 1 TeV of the mass of the WIMP, while the ATLAS experiment is able to extend these limits to lower values of the WIMPs. And of course, with more data, ATLAS will be able to exclude lower interaction cross-section. So also other models are considered, and in particular models which hypothesize a scalar or a pseudo-scalar mediator. And in particular, in this kind of with this kind of mediator, a Yukawa-like interaction of the new mediator with the standard model particles is hypothesized, as you can see from the plot in the left, which is one of the leading diagrams for to target this kind of models, in which you have these coupling between the new scalar or pseudoscalar mediator to top quarks. So these kind of models can be investigated in TT bar plus MET final states, or in general heavy flavor plus MET final states. And in particular, in order to target this kind of model, the events are selected by requiring at least one BJet and 2 leptons, and this is the most sensitive channel. So in order to reduce the backgrounds, a cut on the MET significance is applied, but also on the transverse mass, this variable MT2, which is able to reduce the TT bar backgrounds in an optimal way, since the TT bar background has a kinematic endpoint in this kind of variable. So in order to set limits on these kind of models, being the transverse mass distributions are looked for as the signal region, and this signal region is split for the lepton flavor in order to enhance the sensitivity to these new physics models. So in order to control the TT bar and TT bar Z backgrounds, also in this case, control regions are defined, and these are used to inclusively correct the background normalization. And in this case, the dominant sources of uncertainties are coming from the measurement of the jets, the modeling of the TT bar backgrounds, and the Monte Carlo statistics in extreme phase spaces. So in the middle of the slide, you can see a summary plot, which is showing you the signal regions which are used to set limits on these kind of models. On the right, on the middle, you have some set of validation regions which are used to validate the background estimation, which is performed also using these two control regions on the left, in which you have the normalization of the TT bar and TT bar Z processes. And so, as I said, limits on this scalar mediator can be set, and these are usually shown for fixed value of decouplings and versus the mass of the mediator. You can see how mediators up to 250 GeV are excluded in this case. But as I said, this kind of model can be tested also in other heavy flavor plus MET final states. In particular, it is possible to look for this kind of diagram here on the left, in which you have the production of these WIMPs in association with two BJets. So the events here are selected by using a MET trigger and by requiring two BJets with an efficiency which is around 77% in the case of the working point chosen. So in order to keep the selection as low as possible, a two-dimensional cut is applied on the product of the leading jet PT and MET. And then some BDT discriminants are built in order to discriminate the TT bar and V plus jet standard model backgrounds with respect to the simplified dark matter models which are targeted. And after applying cuts on these BDT discriminants, a final discriminant is built by looking at this cosine theta star BB variable. So also in this case, it's crucial to correct the standard model predictions in control regions, and these are built by looking at Z plus 2B jets events and with the Z decaying to leptons. So in this case, the dominant uncertainty is mainly coming from the modeling of Z plus heavy flavor process. And in the middle of the slide, you can see a summary plot showing all the signal region of this kind of search, which is not targeting only dark matter models, but also other SUSY models. And in particular, the bottom right part is showing you the dedicated signal region to the dark matter search. And on the right, you can see again the limits which can be achieved on the scalar mediator. So it is possible to look also to pseudoscalar mediator, and also the monojet search is sensitive to this kind of signal, like the diagram which is shown in the middle of the slide. But of course, the best sensitivity is achieved by looking at the heavy flavor plus MET final states. So in general, the monojet search is less sensitive because this kind of model has a softer MET spectrum with respect to the standard model backgrounds. But as you can see, it's also able to set strong limits on the mass of the mediator from the bottom left plot, as you can see. So again, it is possible also to convert these results on to compare to other dark matter searches, and it is possible to compare to undirect detection experiments and to set limits on the annihilation cross-section of WIMP pairs into standard model particles. So we have been talking about WIMPs and mass. So it is a good question could be if WIMP does dark Higgs mechanism exist to give mass to these WIMPs. So it is possible to add an additional particle to these simplified models, so these dark Higgs, and its main decay mode will be in a pair of vector boson for large enough masses. So in order to maximize the sensitivity to this kind of model, a fully hadronic final state is targeted by, and the best reconstruction is achieved by looking at these boosted decays of these dark Higgs and by reconstructing the events with larger jet. And then in order to improve the resolution of jet substructure variables, the tracks associated to the jets are corrected by the energy deposit of the larger jet, which is built by reclustering a smaller jet. So the n subjettiness variables are used to discriminate and to look for the four-prong topology inside these star jets, and events which are failing the cuts are somehow included in this intermediate category. So the signal region is given by the invariant mass of these vector bosons, and single beam control regions are used to correct the standard model prediction of V plus jet processes. In the bottom left, you can see a summary plot of the control regions and the signal region, which is split into several beams of missing ET, and on the right you have an example of the most boosted region. And in the end, by fitting all these regions in a maximum likelihood fit, it is possible to set limits on the parameters of this model, which are reported in this plane, in which you have on the x-axis the mass of the Z prime, on the y-axis the mass of the dark Higgs. So this brings me to my conclusion. So today I presented you recent results on simplified dark matter models, and already some results have been already shown by Aleksander, and many candidates of dark matter might be also identified in SUSY models, and latest results will be shown tomorrow by Abhishek. So in general, there is a growing interest towards more exotic signature in ATLAS, as you can see from the many models which are investigated, and this is good because it's pushing our understanding of the detector forward.
Okay, thank you, Guillermo, for the nice talk. Questions? Tanya, please go ahead.
Yeah, again, it's more comments than questions. So can you go to slide 7? I have 2 comments. This is slide 7. Yeah, exactly. Okay, if I look on the right-hand side, I mean, this is quite nice to say how close you get to the theory limit. However, I find it difficult now if you have a model with a similar signature, but you're not looking exactly at the same generation. Yeah, so I know, I mean, I looked a little bit into these results, maybe not this, but previous ones with this scalar mediator and so on. And then if you try to translate this to different models, it involves translating between different UFO models and cross-checking them and seeing whether they give the same result and so on. So I understand that this is nice for you to show how sensitive you are, but I think what would be extremely important, and this can be on HEP data or wherever, I don't know, would be to really give the values you get for this theory cross-section. Because otherwise one has to basically rerun the whole thing in order to understand what the constraints are from this plot. So this is a comment, I think, which you can pass on, because I see this is now a tendency to present results like this in this manner, and I think it doesn't make things easier for people who don't want to do a whole recast, but just want to get the feeling on what is excluded for this in terms of production cross-sections. Yeah.
Yes.
Okay.
I fully agree with you, and that's why the monojet search is also providing model-independent results on the cross-section.
Yeah, I mean, it's really a mess. Yeah, at some point, sorry, but at some point you just have to say either I rerun the code they ran, or I just assume I produce somehow similar results and hope it's correct. And okay, I mean, so the sigma theory for G = 1, I think this is something one needs somewhere documented. And the second thing, can you go to slide 9? Yeah, similarly, I mean, something which looks nice, but again, might lead to misconceptions if one interprets this in different models. On the left-hand side, the plot, I mean, the most sensitive search here is not always the most constraining one, yeah, because it really depends on the theory prediction. So you might go very low, but you have a very, you have different numbers for the theory predictions, and it might be that one of the searches which looks extremely sensitive here, in fact, doesn't really constrain so much of the parameter space. So I think there need to be complementary plots which show this really in terms of constraints which have been shown in previous talks. Again, I know it's not you who is responsible, but maybe you can pass this up the ladder or sideways or whichever direction.
Okay, thanks for your feedback.
Yeah, okay, thank you.
All right, thanks, Tanya. Yeah, indeed, good feedback for the experiments. Okay, thanks again, Guillermo. I think we have to move on now to the next contribution. And we have Krzysztof, we are now switching the focus to the future colliders, the plus and minus collider, and Krzysztof will tell us about searches of invisible scalar decays at CLIC. And I can see your slides. But Krzysztof, we cannot hear you if you are speaking. You are muted.
Okay, sorry. Can you hear me now?
Yeah, we can hear you now.
Okay, sorry. So as it was said, I would like to present you the topic of invisible scalar decays at CLIC. It's a future collider, and the analysis was carried out in collaboration with Filip Zarnecki, Bogdan Grządkowski, and Michał Iglicki. All of us are from Faculty of Physics, University of Warsaw. And this work is already published. Here it's the reference. Okay, so first a few words on CLIC. It's a linear collider where electrons and positrons would be collided. Yes, there are 3 stages of CLIC project, starting from 380 GeV up to 3 TeV, and its length depends on the energy. To achieve such energies, one need a new accelerating scheme. It's something called two-beam accelerating system with drive and main beams. When first we accelerate drive beams, and then by decelerating them, we restore energy to accelerate main beams. As I said, there are 3 stages of CLIC project: 380 GeV, 1.5 TeV, and 3 TeV, and the CLIC would be starting from 11 kilometers up to 50 kilometers long. CLIC offers electron beam polarization of 80%, and unfortunately positron beam is unpolarized. More details can be found here. Now a very short introduction to physics at CLIC. There are several goals of such searches. First, Higgs boson studies, top quark studies as well, then electroweak precision measurements and searching for beyond the standard model phenomena, for example, new particles, new interactions, and so on. And I would like to focus on Higgs physics. So Higgs can be produced at CLIC in two dominating channels. First, it can be Higgs trialing process with production of Z boson and then with emission of Higgs boson. It's shown here, and this process is dominant at 380 GeV. And then at higher energy stages, it can be produced in double W fusion to Higgs, and together with 2 neutrinos. This Z channel allows us for event selection independently on the Higgs decay channel. So we are sensitive to invisible decays because we can reconstruct Z boson and then try to reconstruct Higgs or search for missing mass corresponding to the Higgs boson. So we were searching for such processes. Our signal is described here, so we expect that in the collision of E plus E minus, as Z boson could be produced, then it can emit a Higgs boson, and then Z boson decays into quarks. Of course, it can also decay into leptons, but this hadronic channel is dominant. The statistic is just higher, so we decided to use this signature. And Higgs boson can decay into standard model particles, mainly BB, tau tau, and so on. But we believe that it can sometimes decay also into something invisible, for example, dark matter particles. So our signature is as follows. We expect to have 2 jets consistent with hadronic Z boson decay. As I said, because of higher statistic, we chose hadronic decays. and then missing energy consistent with 125 GeV, so mass of the Higgs, of the standard model Higgs boson. Okay, but of course we have several other processes which are the background for us. Here you can see some of them. For example, Z boson can decay into 2 quarks, 2 leptons, and this 2 jets or 2 leptons are a part of our background. Then also our, let's say, signal process, but when Higgs decays into standard model particle is also a part of the background. We can also have something more complicated, to W's, to Z's, or this process with, already mentioned, with double W fusion to Higgs. But when Higgs decays into standard model particle is also a part of our background. So because CLIC is not running at the moment, so we need somehow simulate the running of the CLIC project. So we started with generation of events with Wizard. It's a standard tool to generate physical events. There are 4 groups of events analyzed by us. So first signal is, as I said, Higgs plus QQ production with Higgs defined as a stable particle. Then standard model Higgs boson decays. So we have Higgs plus QQ, LL, or nu, and we assume that this Higgs decays only into standard model particles. Then we can also include other E plus E minus collision final states. They are listed here. And in our analysis, we also include beam-Strahlung and TPA photon interactions. They are very important at lepton colliders. Okay, we assumed CLIC energy spectra for 380 GeV and integrated luminosity of 1 inverse attobahn of unpolarized beams. And we simulated the detector with Delphis. It's a fast simulation tool. Here you can see an example of our signal. So we expect to have 2 jets from hadronic Z boson decay, and that's all. So we expect to have some missing energy consistent with mass of the Higgs boson. So we just want to have 2 jets and nothing else. So no electrons, no muons, no isolated photons. To assure such signature, we impose some cuts to our generated events. And they are listed here. So we exclude all the events where there are some electrons, muons, or photons with energy above 2 GeV, 3 GeV, and 5 GeV respectively. We demand that energy lost in the jet clustering below is below 10 GeV. This assumption is to assure that reconstruction is complete. Then we want at least 2 charged particles in each jet to exclude false lepton interpreted as jets. 2 jet topology with Y23 and Y34. These are parameters describing distance between jets, and it's a way to have 2 jets, not 3 or 4. And then cut on jet invariant mass between 80 and dijet invariant mass between 80 GeV and 100 GeV, which corresponds to mass of the Z boson, and dijet emission angle, cosine of this angle less than 0.8. And here you can see our efficiency. As efficiency, I mean fraction of the events which pass our preselection. So we have nearly eliminated E plus E minus background, still have more than 100,000 events. We have about 200,000 events for E gamma and gamma gamma interactions. Both, as I said, both beam-Strahlung and TPA photons are included in the analysis. And then standard model Higgs decays are nearly almost negligible, I would say. And then our H when Higgs decays invisibly are at the level of 40%. Of course, here we assume that only that we have only invisible decays of the Higgs boson. Okay, here you can see recoil mass distribution after our preselection. As you can see, here is a visible peak for mass of the Higgs boson, 125 GeV, and these are other channels included in the analysis. Our background is this black curve. It's all the background channels summed is this black curve. Okay, then after our preselection, we made something called selection, just used the boosted decision trees to get final results. Here you can see distribution of the BDT response for signal and the background. Assume that branching ratio of Higgs going to invisible is at the level of 1%, only for the signal, of course. We used 5 variables, and these are results. So the final results are here. So we can say that at the level of 95%, I mean confidence level of 95%, for expected luminosity of 1000 inverse femtobarns and energy of 380 GeV, CLIC would limit invisible decays of the Higgs boson at the level of 1%, of course, assuming that no excess above predicted standard model background is observed. Okay, but similar approach can be used to search for production of new states, for example, new scalars, very similar to Higgs boson, because they could be produced in the same way in E+E- collision and then with Higgs-Ströhlung process. So we can just simulate similar events, just changing Higgs mass, and then try to rerun our analysis. And here you can see results for CLIC at 380 GeV for this new scalars, depending on mass of this new scalar. This is cross-section relative to standard model cross-section for Higgs of this mass. And here we compare results for one inverse autobarn and 4 inverse autobarns, because there are 2 different scenarios for the first stage of the CLIC project. Okay, but we also performed the same analysis for CLIC 1.5 TeV. It was much more complicated because of the background, other background channels, but here you can see our results, these magenta curves and these blue curves compared to results from Opal and from ILC. It's another project of linear collider, and as you can see in this region, we are the best, I can say. Okay, but that's not all, because there is something called Higgs portal models, where new scalar field phi coupling to dark matter particles could mix with the standard model Higgs field thanks to such mixing matrix, and then we would have to mass eigenstate H and H prime. If alpha, this mixing parameter, is less than 1, then H is just standard model like particle, the observed 125 GeV state, but it can also decay invisibly via this component, via this sign squared. But if H prime is also light, then it can be produced in E+E- collisions in the same way, and invisible decays dominate because of cosine squared. We considered vector fermion dark matter model as an example of such Higgs portal model, and here you can see our results on these new scalars translated to limits on sine alpha. This is again mixing parameter of the vector fermion dark matter model. In terms of mass of psi minus, it's particle which could be dark matter in this model. So you can see that our model independent analysis can be translated into limits on some physical models. Of course, there are some assumptions here and of the other model parameters, but you can see that our results for CLIC are below results for CMS and ATLAS, and as well as some other parameters measurements. Okay, some conclusions. As I said, we searched for invisible Higgs boson decays. We used wizard event generation and fast simulation with delphas. We included gamma-induced background in our analysis. We can say that CLIC running at 380 GeV with luminosity of 1 inverse attoborn can constrain the invisible decays of the standard Higgs boson to 1%. Our study can be extended to search for X2 scalars for CLIC running at 380 GeV and 1.5 TeV, and our results can be interpreted in terms of mixing angles of Higgs portal models. That's all, and thank you very much.
Thank you, Krzysztof, for this nice talk and results. Are there questions or comments? Please go ahead. From my side, I actually had two maybe quick ones. So for the standard model Higgs boson result, first question is, I was curious about the variables that you used in the BDT. You mentioned you used maybe 5 variables or something like
yes.
that.
There are 5 variables. I think I have them in the back. Oh, I don't have them. Okay, sorry. Yes. It was missing mass of this. Yes, you're asking about these variables, right?
Right. The 5 variables. Which ones? Which ones are they that went into the?
We used the mass of this. Right. This missing mass, mass of the Z boson, and some transverse momenta, I think.
Okay, I see. And then that, okay, then that I guess makes sense. Then it gives improvement with respect to only using the missing mass. Yeah. And then the second question I had, you did mention that the beam strahlung is quite important here. Actually, maybe I don't know if you have a quantified number. I was wondering what would be the effect of the numbers that you've showed today if one would simply neglect the beam strahlung.
Okay, we performed such analysis, and the results, these final results, was at the level of 0.9%.
Okay.
So it's about 10%. I mean, difference, 10%.
Okay, I see. Okay, yeah, that's exactly what I wanted to know. Okay, sounds good. Thanks, Krzysztof, again for the nice talk.
Thank you.
And we can move on now to Aleksander.
Yes, hello. Can you see me? Yes.
Yes.
I will try to share my slides. And do you see them?
Yeah, we can see you. We can see the slides, and we can hear you.
Okay, so let's start. Hello, my name is Filip Zarnecki. I am also from the Faculty of Physics, University of Warsaw, and within our small group, we have made a study of the dark matter searches with mono-photon signature. Let me just start from some motivation. This is very similar to the monojet study, which was already mentioned earlier today. When we look for a production of dark matter at plus and minus colliders, well, this final state is not visible in the detector, so we need some tag. And the photon emitted from the initial state is very efficient and very convenient tag, because first of all, it's a process we know very well, and the predictions are very precise, and also the backgrounds are well understood. So we consider this monophoton signature as a signal for dark matter pair production at ILC at 500 GeV and CLIC at 3 TeV. So let me just briefly summarize the properties of these two collider projects. ILC technical design was presented in 2013, and the current proposal is to construct this accelerator in stages, starting from 250 GeV Higgs factory, and then going to 500 GeV and possibly also to 1 TeV. We assume that both electron and positron beams will be polarized. For CLIC, we can go to much higher energies, as Krzysztof already mentioned, with the two beam accelerating scheme. Unfortunately, here what is considered is only the electron beam polarization of 80%. So the following running scenarios are considered in our analysis. For ILC, we assume this is the so-called H20 scenarios, which was optimized for the physics reach of the project, taking into account different analysis. And in this scenario, there are the main part of 4 inverse attobars, which are assumed to be collected at 500 GeV, will be taken with left-handed electrons and right-handed positrons, or right-handed electrons and left-handed positrons. This is what I denote as LR and RL combinations, and just smaller amounts, 10% each, will be collected with same polarizations of electrons and positrons, so RR and LL combination. And for CLIC, the 5 inverse attobars, which are expected to be collected at 3 TeV, will be mostly devoted to running with negative electron beam polarization, and only 1 inverse attobar with right-handed electrons. So there were already many studies of this signature at +E- colliders. There are two most recent studies from ILD and CLIC are mentioned here. You have the references from last year and this year. However, all these studies focused rather on heavy mediators, where the production of dark matter particles goes through the heavy mediator exchange, and also when the couplings of this mediator are of the order of 1 or of the order of electroweak coupling. So the EFT approach was basically used, and what was extracted were mainly limits on the dark matter masses or mediator masses. We wanted to address this from another perspective, and we focus in our study on light mediators, so on processes going through the light mediator exchange, and processes where the coupling of the mediator to the standard model particles is very small, so much smaller to the coupling to the dark sector. Also, we try to present our results in a most model-independent way possible. Namely, we try to extract limits on the production cross-section as a function of the mediator mass and width. And it turns out that then they depend very weakly on the details on the model. So the final technical issue is the way we simulate the mono-photon events. Here I don't want to go into details. You can find them in the work listed here, published last year. But the important issue is when simulating these events is with Wizard, where is that we want to simulate the detectable photons in the matrix element using matrix elements, so exactly, whereas the photons which are generated from the ISR structure functions and which has to be switched on to get the proper cross-section calculation should be somehow suppressed in the region where they can enter the detector. So we divide our phase space for photon radiation into 2 parts, one which is simulated with matrix elements and one which is only simulated with the ISR structure function. And this is done in these 2 variables, Q minus, Q plus, listed here. And this boundary is indicated by this dashed red line on this right plot. So you clearly see that the photons which enter the detector in this upper right part are only those simulated on the matrix element level. So for details, you can have a look in this work. We simulate both signal and background events. Even if we finally require only one photon in the detector, we simulate final states with 1, 2, or 3 photons on matrix element level. And all these photons have energy above 1 GeV, and this variables Q plus, Q minus above 1 GeV. And at least one photon is required to be, as we call it, detectable. So has to transverse momenta above 2 GeV for ILC or 5 GeV for CLIC, and to be within the acceptance range of the tracking detectors. And then we use the fast detector simulation framework DELFAS to simulate performance of the ILC and CLIC detectors. And the final requirement is that there is exactly one single photon reconstructed in the detector in the range, kinematic range presented here, and no other activity above the reconstruction thresholds. So let us first look how the simulated background distributions look. There are two background channels which are relevant here, the radiative Baba scattering and the radiative neutrino pair production. And for monophoton events, the whole kinematics is described basically by two variables. We choose PT of the photon and rapidity of the photon, and on these plots, you show the distribution and the rapidity versus logarithm of PT for ILC and at 500 GeV and CLIC at 3 TeV for combined backgrounds. As you can see, the background is mainly in the region of low PT and large rapidities. On the other hand, if we try to simulate a signal processes with dark matter pair production with light mediator, here on this plot we consider 400 GeV mediator at 500 GeV ILC or 2.4 TeV mediator at 3 TeV CLIC, you can clearly see that due to the radiative return process, we have a very large amount of high energy, high PT photons reconstructed in the detector. In both cases, this structure is very, very clear, showing that we have very different shape that it's observed for backgrounds. So just by comparing the observed distribution, two-dimensional distributions of the reconstructed photons with signal and background hypothesis, we can extract limits on the dark matter pair production cross-section. So shown on these plots are limits on the radiative cross-section. So for the limits on the cross-section with production of hard photon, which can be detected in the detector. And these limits, as you can see, they depend significantly on the polarization of the beams. It's clearly for this model with vector mediator, best limits are observed for right-handed electron and left-handed positron beam at ILC, just because the backgrounds are smallest there. The neutrino pair production background is suppressed most. And you can see that the limits are of the order of 1 femtobarn, similar also for CLIC. And then we can also take into account the probability that the process of pair production will result in radiation of the hard photon. And then when we compare, when we correct for this probability, we obtain limits on the total dark matter pair production cross-section. And these limits are of the order of 10 femtobars. Now I present combined limits, so combining all polarization combinations, but for different widths of the mediator. As you can see, for light mediators, limits clearly improve with decreasing width. So it's clear that it's much easier to observe narrow mediator resonance than the wide one, but also you can see that the limits are significantly weaker when we are at resonance, so where the center of mass energy is close to the mediator mass. Then the radiation of hard photons is significantly suppressed. And we also took into account the possible systematic uncertainties. And here you can see that as for heavy mediators, this significant systematic effects are quite significant. Then for light mediators, where you do see the resonance over the flat background, this influence of the systematics is visible, but much smaller. So finally, we also translated this cross-section limits into the limits on the mediator couplings to the standard model particles. This is somehow to verify our initial assumption that we assume these couplings are small, and we can see that we are sensitive to the couplings of the order of 10 to the minus 2, 10 to the minus 3, and this limit is basically only weakly sensitive to the width of the mediator and to the mass of the mediator. It's basically on the same level for all light mediator scenarios. When we calculate limit on the product of the mediator coupling to the standard model particles and dark matter particles, then this situation is slightly different. The limits depend on the width of the mediator, clearly, but they still hardly depend on the type of the mediator. So here you have the limits compared for vector, scalar, pseudoscalar, and axial vector mediators. These limits are basically the same. And also at large masses, the limits no longer depend on the width, which corresponds to the transition to the EFT approximation. So to summarize, we have developed a new framework for mono-photon analysis at the plus-minus colliders, where we focus on a light mediator exchange, and we try to test very small mediator couplings to the standard model. And we showed that both ILC and CLIC will be sensitive to such scenarios. Limits on the radiative dark matter production cross-sections are of the order of 1 femtobarn. Limits on the total dark matter pair production cross-section with light mediator are of the order of 10 femtobarns. The limits are significantly worse for the resonance region. Then above the resonance, they still are of the same order. So we are sensitive to the couplings of the order of 10 to the minus 3 to 10 to the minus 2, and these limits are largely independent of the assumed mediator type or coupling structure. And these limits are also consistent with the earlier limits from EFT type analysis. Thank you very much for your attention.
Thank you, Philip. Thanks for this nice summary. Are there any questions or comments? Please go ahead. I do have 2 questions. One on the simulation of the signal. Maybe this was on slide 8. You mentioned the details, but just for me to understand, so you actually generate a sample with photon at matrix element, maybe using Wizard, but without any of the ISR effects.
No, we have the ISR switched on in Wizard, so ISR is always included.
Okay.
But we then within Wizard we add the dedicated cuts on matrix elements photons to restrict them to the region above this red dashed line.
Okay.
And additional selection criteria, because it cannot be done on the cut level, because of the cut level Wizard does not generate the transverse momenta of the ISR photons yet. But then after the generation of the events, there is a selection stage where we remove events in which any ISR photon was emitted in this matrix element phase space. So at the end, we have both ISR photons and matrix element photons, but they are in with different phase space regions.
Okay, I see. So there is no
to avoid any double counting.
Right.
And we checked with the KKMC Monte Carlo, which gives a semi-analytical simulation of these events, that this approach gives a very good agreement with the semi-analytical simulation for radiative new events. So we are quite sure that this procedure works correctly.
Okay, thank you. And then one more question. I was just wondering, maybe on slide 15, or when you were basically showing the final limits, this model dependent kind of on these couplings. And I was wondering, in terms of if you have an idea, how do these limits compare in general to the ones that, let's say, we produce or project at the high luminosity LHC for these monophoton types of searches, comparing the, for example, ILC or CLIC to the high lumi LHC projections? Do you know
as far as I know, I have not seen any monophoton limits from LHC. There are monojet limits.
I think there was a monophoton, but only using part of the round 2 data. There was a monophoton.
Okay, the limits which maybe I missed something, but as far as I remember, at least from example, the comparisons which were made for the European strategy, there was such a nice comparison, but then it was clearly written that for LHC we compare monojet limits from LHC with monophoton events from E+ E- collider. So you can still compare it, and it seems to be similar order, but in fact you compare very different processes. It could be that if you have a mediator which has only electroweak couplings, it will it can look, it's not, this comparison has really to go then to specific model to be able to compare.
Right, yeah, makes sense. Okay, thanks a lot, Filip, again.
Thank you. I stop sharing.
And we now go to the final contribution for today's session, to Jan. Jan, can you please share your slides?
Hi, yes, I will try to share my slides now. Okay, you should see it.
Yeah, we see the slides.
And can you see the slide changing?
Yeah.
Great. Okay, so hello everyone again. I would like to show you the prospects for discovering the inner doublet model particles at CLIC at its higher energies. And about CLIC, I think it was pretty well covered in talks of Krzysztof Mekala and Filip Zarnecki. So let me just recall that the main focus of those two high energy stages 1.5 and 3 TeV running scenarios are devoted to searching for beyond standard model physics. So this is where our focus will be. And now going to the inner doublet model. This is, as many models mentioned before in this session, this model takes advantage that there is still plenty of room in the scalar sector for new physics. And apart from this standard Higgs doublet, it introduces additional doublet with 4 new scalar fields that do not couple to standard model fermions. And the lightest of them is stable, this neutral age, which makes it the perfect dark matter candidate. This is all thanks to this additional Z2 symmetry. And after fixing the standard model parameters, we have already some existing, we have only 5 free parameters left. So this is all nice and simple. And we have already some existing constraints, both experimental and theoretical in this model. But we need some benchmark points in this parameter space. And these were covered in this paper here. and there were selected benchmark points from the scan over whole available parameter space. This was done for the two possible production scenarios at lepton colliders, one neutral scalar per production and one charged per production. You can see the benchmark points here on the plane of the masses of the dark scalars. Blue points are the selected benchmark points, and the yellow points are all points considered in scan. This is on the right hand side, this is the same, but on the plane of mass differences. And important to notice here is that some points lay in this region of low mass differences. So in particular, when we have such a decay, when difference between masses of those two heavy Higgses is low, this W will be produced off shell. And from those benchmark points considered and selected and described in this paper, we take 23 benchmark points with the highest masses of the dark scalars. And this is because there was a previous study devoted to searching for the IDM scalars conducted in the leptonic channel on the generator level with cuts reflecting the detector acceptance, and this is described here. And here on these plots you can see the results of this study. So sorry. So the expected statistical significance of the deviations from standard model background for each of the considered benchmark scenarios, and this is shown as a function of of sum of the neutral scalar masses, and on the right hand side as a function of two masses of charged heavy Higgs. And as you can see, this is the discovery reach is limited here up to 500 GeV and here up to 1000 GeV. And in terms of cross section, this is a limitation by about 1 femtobarn of production cross section. Sorry again. So this analysis is performed in the semi-leptonic channel because it offers about 1 order of magnitude higher cross section, and it is only possible in this charged scalar per production. So we expect 1 lepton electron or muon and a pair of jets in the final state, and we use some simple cut-based preselection followed by a multivariate analysis for which we use boosted decision trees. And for the sample generation, we used CLIC beam spectra, both for 1.5 and 3 TeV, with corresponding total integrated luminosity of 2 and 4 inversed attobarns, taking into account minus 80% beam polarization. And they were generated using Wizard 2.7. And then for detector response, we use full CLIC model description with round 4, and we simulate this response for 5 selected scenarios. And then we extend the study to all 23 benchmark points considered in analysis. And for that, then we use fast simulation. Here I want to show you also the distributions of the variables describing jet kinematics. So the mass of the dijet system and the energy of the dijet system. And here the black histogram shows the standard model background, and blue and red histograms correspond to the signal scenarios. So what is important also here that this red signal scenario corresponds to a very low difference between scalar masses, and the W there is highly virtual, while for the blue histogram W is real. So you can see that there is a huge difference between those two types of scenarios, and it will require special treatment, which I'll show you later. These are the results of the analysis involving full simulation. So these are the expected significances for each of the 5 signal scenarios considered in this study. And as you can see, all of them, for all of them, the dark scalars could be discovered. However, worth noting is that here the multivariate selection is optimized for particular scenario, which means that the BDT training is performed separately for each of the scenarios. So now let's see what will give us the approach with DELFAS, with the fast simulation. But there is one important issue here with DELFAS, namely it is connected to the fact that at CLIC we have high beam intensity and high bunch rate, which results in huge beam-induced backgrounds. And the most important are the gamma-gamma interactions producing soft hadrons. And the standard procedure to reduce this background is to apply cuts on timestamps of the particle flow objects. And this is important in this analysis because, as I mentioned, we have those scenarios with production of the virtual W, which decays into particles that carry very low momenta and energies. So the reconstruction of these objects is highly influenced by this soft gamma-gamma to hadron background, the so-called overlay background. However, this background and those timing cuts are not implemented in DELFAS CLIC model. So we include this background and we apply the cuts on the generator level, the effective cuts that effectively mimic those timing cuts on PFOs. And these are the effects of this approach. So you can see here the distributions of mass, again, of the digest system and the mass of single jet. And these are shown for with light blue histocolor. You can see the histogram corresponding to just pure DELFAS without any overlay contribution. And with the dark blue color, you can see the histogram resulting from DELFAS after taking it into account the overlay background. And this is compared to the full simulation, which is shown with red line. And also you can see that this is shown for the signal scenario where again W is far off shell, so there is small scalar mass difference, and the influence of the overlay is huge. But you can see that that the improvement in agreement between fast and full simulation after our improvement after our inclusion of this gamma-gamma hadrons background is significant. These are the effects on the final results, so on the expected significances. Here you can see the same results from the full simulation as previously with the red circles, but now there are shown also the results that we obtained with just DELFAS, and these are with the blue crosses. And with green dots, you can see the results obtained after including the overlay background. So you can see they are much closer to those from full simulation. So we can say that they are much more realistic predictions. And finally, these are the all of the results. So the expected significances for all of the considered 23 benchmark scenarios for both energy stages obtained with DELFAS with the contribution of the gamma-gamma to hadrons background. However, now the training was performed for all of the available samples, for all of the available scenarios, but separately for the scenarios with the offshore W boson production, and separately for those where the W is real, because of their different signatures. And again, you can see that most of the considered scenarios could be potentially discovered at CLIC, apart from those two, considering both energy stages. And this brings me to my summary. So I can say that we analyzed the prospects for discovering the inner doublet model scalars at highest energies of CLIC, and we used for that both full and fast simulation, where for the fast simulation we extended the CLIC model for delphas such that it included gamma-gamma 2 hadrons overlay events. And I can say, and the conclusion is, and I hope that I convinced you, that the charged IDM scalars can be discovered at CLIC for their masses up to 1 TeV. And that's it. Thanks a lot.
Thank you, Jan. Thanks for the interesting talk. Questions, comments, please raise your hand. If not, I actually had two practical questions. So it's very interesting that how you included this gamma-gamma hadronic kind of background, like beam events. Just one thing, if I understood correctly, so if one runs Delphis now with your implementation, would one get this by default? You know, like the using the cards, or there's this CLIC det model that needs to be run in parallel to overlay the events together?
I mean, so what you need is basically, yes, you need our implementation of the CLIC det card. So that's one thing you need, but this is a very simple modification.
Right.
But other thing you need is the so-called PyLab file, which is designed for LHC, and it is designed to include PyLab in LHC. But you can produce it using the samples of the gamma-gamma 2 hadrons events, and this is what I've done. And what you have to do is to include this file in the simulation process. So
okay.
You need this file.
Okay, I see. And then just one curiosity, actually, how slow is the full simulation for CLIC? Is it let's say I'm assuming it's substantially slower than Delphis. That's why people don't use it for general analysis, no?
So you ask how much slower is full simulation compared to Delphis?
Right.
I don't know if I can answer this correctly, because I run full simulation on grid and Delphis on my personal computer, okay. But I think I think it's where after inclusion of these overlay events, it's starting to be comparable. At least this last step that in which you reconstruct objects and save it to root tree and things like that.
Okay, yeah, makes sense. Okay, I don't see any other raised hands. Thanks again, Jan, for the talk, and yeah,
thanks a lot.
Yep, thank you for all the speakers for the session today, as this was the last talk. Just to say, we have our next session tomorrow morning, 8 a.m. I think, New York time, and hopefully we'll see you all there. Thanks again for today, and yeah, see you tomorrow.
Thank you. Goodbye.
Thanks a lot. Bye-bye.
Bye-bye.
Thank you.